So today, we will jump into the goals of the course and the logistics of the course, and also talk a little bit about what multitask and meta-learning is and why we might want to study it. Before we get started, I want to make some introductions. So my name is Chelsea. I'm the main instructor for the course, and we also have 7 really awesome TAs. Great, so I'd love to welcome you to the course, and I guess as a first question to get a sense where everyone's at, how are you doing? If you want to answer briefly, do you want to raise your hand and share how things are going? Yeah.
Good, but my first class, I went to the wrong class. That was interesting how, like 5 minutes into class, I saw the title and I see public policy when I was supposed to be in AI.
Great. Well, I'm glad you made it to the right class this time.
Yeah.
Anyone else? Yeah.
Didn't realize classes were like 30 minutes away, so I got my dorm like 10 minutes for class.
Cool. Good to figure everything out. Anyone else? Okay, well, I guess one thing I wanted to share or say is that it feels great to be closer to something that's a little bit more normal. And that's really awesome. I'm really excited about that. At the same time, it's not like it's like there's lots of other stuff going on in the world right now that's not great, and so we acknowledge that, and we try to set course policies that give you a little bit of flexibility in the course, and recognize that this course isn't the only thing going on in your lives, and so hopefully those policies will help with that. Great, so we have a lot of information and resources about the course. Your first place to go is the course website. We put a lot of information here, so please read through it. And if you have any questions, make sure that you read through it first, but then feel free to post any questions that you have on Ed. Ed is connected to Canvas, and you can also reach out to the staff mailing list as well. We encourage you to post any questions that you have to Ed, because that makes it so that other students can see your questions, because other people probably have the same question as you. But you are allowed to make a private post on Ed or email the staff mailing list in cases where you don't want it to be shared with others in the class. For example, if you have an OAE letter, you can send this either to the staff mailing list or in a private Ed post. We also have office hours that are all posted on the course website, and the Zoom links are on Canvas, and office hours will start on Wednesday. Cool, so what will you learn in this course? There's really 3 main things that we're going to hope you'll be able to learn in this course. The first is the foundations of modern deep learning methods for multitask learning and generally learning across tasks. The second is not just learning about those methods, but actually getting experience implementing them and working with them in code and in PyTorch, and trying to understand how these systems actually work in practice beyond just how they are supposed to work from lectures. And lastly, I also want to try to give you a glimpse of the process behind actually building these kinds of methods. I think that a lot of courses will present you knowledge and present you ideas as they are, and not actually talk a little bit about the scientific process and the engineering process of arriving upon those ideas. And I'm hoping that maybe by giving a little bit of a glimpse into the process of building these algorithms and understanding these algorithms, that will encourage you to not take them as them is, to challenge them, and also to help you learn about the process of developing these kinds of algorithms in the first place. Cool, so along those lines, we'll cover a wide range of topics in the course. We'll start with kind of the basics of multitask learning and transfer learning. We'll move into 3 broad classes of meta-learning algorithms, including black box approaches, optimization-based approaches, and metric learning. We'll also cover more advanced meta-learning topics such as overfitting in meta-learning, unsupervised meta-learning, and Bayesian meta-learning methods, before moving into other approaches for few-shot learning and adaptation, including unsupervised pre-training and domain adaptation and domain generalization. All throughout this, there'll be an emphasis on deep learning techniques, and we'll also study a number of different case studies in real applications. This includes things like multitask learning in recommender systems, like the recommendation system behind YouTube. Also, meta-learning for land cover classification and education, as well as few-shot learning in large language models. Now, one thing that's a little bit different from the last time we offered this course is these topics right here are all new to the course. And one thing that's different is we're not going to have any lectures or homeworks that cover reinforcement learning topics. And so essentially, we're removing the reinforcement learning topics from the previous quarters and adding in this new content, including few-shot learning with unsupervised pre-training, how this relates to foundation models, as well as domain adaptation and domain generalization. Now, you might ask, why are we removing the reinforcement learning content? What if I want to work on reinforcement learning? For that, we're introducing a new course in the spring quarter on deep reinforcement learning that I think will do a nice job of complementing some of the other reinforcement learning offerings on campus. Removing reinforcement learning will also make the course more accessible to people who don't have a lot of background in reinforcement learning. We found that in the previous quarters, just one kind of refresher on reinforcement learning often wasn't enough to get to the more advanced topics. That said, if you're really excited about applying some of the ideas in the course to reinforcement learning topics, you can still explore that in the final project and get support from the course staff, many of whom also are very familiar and experts in reinforcement learning problems. Awesome. So for lectures, all the lectures are in person. They're also live streamed and recorded, and you'll have access to the recordings on Canvas. We're also going to have 2 guest lectures as well around the end of the quarter, and those are not fully sorted out yet, but we'll announce those shortly. I really encourage you to ask questions during the lecture. This serves a lot of different purposes. You can ask questions by raising your hand. You can also ask them by entering questions in the Zoom chat, and we have a TA who will monitor the chat and make sure those questions get answered during the lecture. I find it really helpful when people ask questions because it helps me understand and gauge if you're understanding what I'm saying. And if you don't understand something, some concept, or want to learn more, or I'm not covering something important, that's my fault, that's not your fault, and chances are other people have the same sort of misunderstanding. And so if you ask that question, that will help everyone in the course and help me help you, basically. My goal is to help you learn the topics in the course rather than standing up and listening to myself speak. Office hours will have a mix of in-person and remote, mostly in-person, but there will be 2 remote options, especially for SCPD students who are in the course. Great, and then prerequisites. The main prerequisite is to have sufficient background in machine learning, so something like CS330 or equivalent, because we'll be building a lot on the basic concepts of machine learning, and we're not going to kind of cover topics like cross-validation, training sets and test sets, and so forth, or the basics of neural networks. All the assignments are going to require training neural networks in PyTorch. If you really hate PyTorch for whatever reason, you could implement the assignments in some other framework. But all the starter code is in PyTorch, and you'll be able to get more support if you do everything in PyTorch. So we'd encourage you to do it in PyTorch. A few quarters ago, the course used TensorFlow instead, and people seem to really like the switch to PyTorch. But hopefully, yeah, we provide some flexibility there. We're also going to have a PyTorch review session on Thursday at 4:30 p.m. in this room. And so if you want a refresher or some get some of the kind of concepts in PyTorch that will be useful for the assignments, you can come to that review session. It will also be live streamed and recorded on Zoom as well. Cool. So digging in a little bit more into the content, we'll have a number of different assignments. The first assignment is just going over, it's basically just a warm-up to make sure you're familiar with PyTorch and going over some of the basics in multitask learning. Then we'll start to go into our core assignments. The first one will be on black box meta-learning and how do you set up the data to make few-shot learning with these black box models more effective. The second will go into gradient-based meta-learning and metric learning. Both these assignments will include kind of few-shot character recognition kinds of problems. And then the third homework will go into fine-tuning pre-trained models with an emphasis on natural language processing and language models rather than image recognition. And then the last homework is going to be optional, and it's going to cover some more conceptual aspects of the course. So the first 4 homeworks are all going to be implementation-based, whereas this last homework will be just kind of solve paper. The grading for the course is 50% homework, 50% project. The first homework is just a warm-up, so it's only 5% of the grade, whereas the next three homeworks are each 15% of the grade, so this adds up to 50%. I mentioned that we wanted to provide some flexibility to students in the course, and so if you complete this fourth homework, it can be used to replace one of the previous homeworks, or it can be used to replace part of the project grade. And if you do it, we'll always do whatever is best for your grade, and so if you don't do well on that homework but you still try to complete it, then it won't hurt your grade, it will only help. And then the second aspect of giving some flexibilities, we'll give 6 late days across homeworks and project-related assignments. You can use up to 2 late days per assignment. No questions asked. Anyone can use these up to the 6. Of course, if you have other extenuating circumstances that make it difficult to submit courses on time, then feel free to send us a note, send us an email, and we may be able to make accommodations beyond these 6 late days. Great, and then lastly, for the collaboration policy, please read the course website and the honor code. For the homeworks, you're allowed to talk to other people about the homeworks, but you should document your collaborators, and please write up the homework solutions on your own without referring to other student solutions and without referring to solutions on the internet. Cool. For the final project, this is basically the main parts of the course are, in terms of your work, are the assignments in the project. The project is a research level project of your choice that you can do in groups of 1 to 3. If applicable, if you're doing research on campus, we really encourage you to use your research for this project, and as long as it's applicable to the topics that are covered in the course. And you can also share the project with other courses, although we'll have slightly higher expectations in that case. And then same late day policy as the homeworks, but there's no late days for the poster session because the poster session will be a live event, and you can't, there won't be a late poster session or anything like that. And the poster session is on December 7th, which is basically the last day of classes, which we'll have instead of a lecture. Cool. So any questions on course logistics? Yeah.
What type of topics can we work on for the final project?
Yeah, so I mean, basically, the question is what kind of topics can you work on for the final project? Basically, whatever you want, as long as it pertains to the course content. It's very open-ended. I guess one other thing that I can mention there is that we are soliciting ideas from the broader Stanford AI community, and so we'll post a list of ideas for the project on Monday next week. And so if you're not sure what kind of project you want to do, you can look at that list for some nice ideas. But if you have something in mind already, or if you want to be creative and think of something else, it just needs to pertain to the topics of the course. We also have detailed guidelines on the project and what we expect posted on the course website, and so you can refer to that document for a lot more details. Yeah.
Examples of what people have done in the past for their course project?
Yeah, that's a great question. So we haven't posted examples yet, but we want to post some examples of some previous projects. One thing that you can see already is that if you look at a previous offering of the course, I think it was 2 years ago, we posted titles of all the course projects, and then some of them have links from students who are willing to make them public. And so you could already take a look at that, although we're planning to provide some more explicit examples in the coming week. Cool. So in terms of initial steps, homework 0 has already been posted. This should be pretty lightweight. It's due in a week. All the assignments are due at 11:59 Pacific time. And I'd encourage you to start trying to form groups if you want to work in a group. And making posts on Ed and so forth can be helpful for that. And we're also happy to try to help you connect with other students in the course as well, if that would be helpful. Yeah.
Strongly recommend working in a group, or do you have reasons why you might want to or might not want to work in a group?
Yeah, I think that there can be pros and cons to working in a group. I think that the benefit is that there's a little bit more that you can do in a group, and you might also have complementary expertise. It can also be fun to work with other people. The downsides is that you are kind of relying on other people a little bit, and you want to kind of make sure that the people you're working with are you're kind of compatible and can rely on them to some degree. Generally, we recommend it, but it's certainly not required, and you're welcome to work alone. Cool, so let's dive into why we might want to study multitask learning and meta learning. So the first thing I'll cover here is a little bit of my perspective and why I find multitask learning and meta learning really cool and exciting. And in particular, a lot of the research that I do in my lab is trying to think about this question of how we can allow agents to learn a breadth of different skills in the real world. And what I mean by agents is actually working with real robots and allowing them to learn skills like this. So here I'm holding the block in front of the robot, and it's learning to place the red block into the shape sorting cube. But not just something like that, being able to do something like watching a video of a human place an object into a bowl and having the robot figure out how to do the task as well. Or by figuring out how to use tools to complete a task, even if it's not explicitly told that it should use that tool to complete the task. And I think that robots are really cool and interesting because I think that they can teach us things about intelligence. They are faced with the real world. They aren't just kind of looking at images in a static. They actually have to contend with the complexity of the real world. In order to be useful in the real world, they have to generalize across lots of different tasks, objects, and environments. And I think they also need some sort of common sense understanding. They need to understand what will happen if they try to pick up objects or try to move their arm in a certain way. And then the last thing is it's not clear exactly what the supervision should be here as well. And I guess beyond these two things, beyond trying to teach us things about intelligence, there's also this aspect that if we can actually build robots that are very useful, then they can help out in a wide range of aspects of society, where people are doing jobs that are dangerous, or people are doing jobs that are tedious, or jobs that they would rather not be in. And so, I guess from that standpoint, I would like to tell a little bit of a story, which is that at the beginning of my PhD, I was a PhD student on the other side of the bay. And I was working with this robot right here. And this is a project that was happening. The robot was learning through trial and error. It was trying to figure out how to insert the wheels of this toy airplane into the corresponding hole. And what you can see is that at the very beginning, it didn't really know anything about the task. And over time, it gets better and better at trying to figure out how to kind of assemble this part into the plane. This seems pretty cool. I found it like really, really cool to see this whole process. But one caveat here is that the robot effectively had its eyes closed. So the robot couldn't actually see anything. It wasn't using the camera in any way. It was just using the position of the joints. And so the next step that I really wanted to explore in a follow-up project was to think about, can we allow the robot to complete these kinds of tasks, but with its eyes open, and actually use vision in order to solve these tasks? And this was the resulting project. And here we were trying to learn a neural network policy that maps from images taken from the robot's camera directly to torques applied at the robot's joints. And you can see that over time, it's getting better at the task. At the beginning, it was just moving its arm around pretty randomly. And it gets closer and closer to inserting the block into the red hole. And not only can it insert the block in the red hole for one position of the cube, but it can do it for multiple different positions of the cube. And this is why it needs vision in order to succeed. So this is pretty cool. These days this maybe isn't that impressive, but 6 years ago, no one had really ever applied neural networks for this kind of task before. And here's actually kind of the result of the final policy. So you can actually see the robot's perspective right here, and we can see that if I held it in different positions, the robot was able to insert the block into the correct place. This is pretty cool. Now, I think what was exciting about this wasn't that the robot had figured out how to do this one particular task, but rather that we had a reinforcement learning algorithm that could allow robots to do lots of different tasks. And so if you took the same exact algorithm and gave it a different reward function, then it could figure out how to do other tasks. So it could figure out how to place the claw of the toy hammer underneath the nail. Or if you gave it a task right here, it could figure out how to screw a cap onto a bottle. And as an example of one more task, this is in a follow-up work, we got the robot to use a spatula to lift an object into a bowl. This last task is actually surprisingly challenging because the robot has to fairly aggressively maneuver the spatula underneath the object in order to lift it up. So this was really exciting. This was like first or second year of my PhD that we got the robot to do these kinds of tasks, all with learning neural network policies. And other people used the same kind of algorithm and built up on it, extended it to other tasks and to other robots to learn things like hitting a puck into a goal, like opening a door, and like throwing an object to hit a target. And around the same time, people were also using deep reinforcement learning algorithms to play Atari games and to play the game of Go and to learn how to walk in simulation. So in general, around kind of 2016, 2017 was a very exciting time for reinforcement learning and for deep learning. The catch, though, is that we have a bit of a problem here in general. So it was all very exciting progress, but there was this problem that in each of these cases, when we trained the robot to do a task, like when we trained it to lift the object into the bowl, we didn't train it to use spatulas generally and how to lift objects into bowls, but we trained it to lift that particular object with that particular spatula into that bowl. And so if you gave the robot a different spatula, put it in a different environment, the robot wouldn't successfully complete the task. And this is a huge problem because it means that if we actually want to put the robot into real-world situations, it hasn't learned something that will actually work in general. And you might say that, OK, maybe we can just give the robot a lot more spatulas and train it with more data. But the tricky part is that when you train these systems behind the scenes, if you actually look at the learning process, often it looks something like this, where the robot attempts the task, and then it needs to attempt the task again. And so for it to attempt the task again, you need to actually kind of put the environment back to where it was, and so that it can attempt the task again from that state. In this video, this is my friend Yevgen. And one of the things you probably notice here is that Yevgen is doing more work than the robot is doing. And this doesn't seem like maybe the right way to be going about things. It importantly doesn't seem very scalable. It's not practical to collect a ton of data in this fashion. And so this is starting to get into why multitask learning and meta-learning matters, which is that we're training these systems to do one very narrow thing, and this very narrow thing requires detailed supervision, a lot of extensive human effort in order to get the system to do that one particular thing. And then if we want to do something else, we also need again, a lot of human effort to train from scratch on that new thing. And this isn't just a problem with reinforcement learning and robotics. And so if you look at problems in kind of speech recognition or object detection, these systems are trained on more diverse data, but they're still learning one task starting from scratch with a lot of supervision and engineering for that one task. And so I'd refer to all these systems as kind of specialists. We're training a machine learning system to do one thing. And what in many cases would be more useful is systems that are not trained on a single task, but on many different tasks. And so, for example, if we look at what people can do, people aren't trained from day one to lift up spatulas, use spatulas to lift up objects, but they're trained to learn much more broadly about things in the world. And in that sense, I would refer to humans as generalists. And I'm interested in this question of how we can build machine learning systems that are more general. And I guess as maybe one more note on this, if you take a system like AlphaGo, which became kind of champion at the game of Go, this is another example of kind of a specialist system. And it's maybe somewhat analogous to training a baby on day one to try to figure out how to play Go without teaching them lots of other things about the world. And in fact, it turns out that even like training a robot to pick up Go pieces and place them into the configuration is actually still beyond the capabilities of of AI systems. And so when you watch, maybe if you ever watched any of the AlphaGo matches, you'll notice that the AlphaGo player is a human who's just watching this computer screen and lifting the pieces for the system. Cool. So that's my perspective in terms of why I'm excited about these algorithms. I guess any questions on all that before I move on to things beyond robots and general purpose machine learning? Yeah.
So you might go into this question in like the next section, but the question has to do with all of the work that's happening on these large pre-trained models now, especially in NLP, where maybe the models are kind of implicitly learning a lot of tasks internally. So would you say that it's still important to kind of explicitly teach a model how to like encode a bunch of these different tasks, or can the implicit learning kind of get us to where we need to go?
Yeah, so the question is about, like, a lot of these large pre-trained models are trained on very broad data sets, and they aren't explicitly trained to do multiple tasks, but they're implicitly trained to learn very broad things. And in some ways, I would, I guess we'll talk about this a little bit later in the course, but there are ways to connect that to multitask learning, and I kind of view that as an example of something that's more of a generalist rather than something that's learning one very narrow task. And so we'll definitely connect to that. And I think that also gets to some of the motivation behind using trying to train generalist systems as well, which is that if we can train a pre-trained model on very broad data and have it learn something more general about the world, then if we want it to do something narrow after that, we can use that as initialization. We don't have to start from scratch. We can start from this more general understanding of the world and use that as initialization to learn much more quickly for a new task. And so some of the two of the lectures that we're adding this year will be precisely on training these pre-trained models in a more general way with unsupervised pre-training, and then fine-tuning them with a small amount of data to a new task. Yeah.
So for a lot of these NLP models, the pre-training task is like fill in the blanks training in a way. So when you're thinking about robotics, how do we think of the tasks that would be like the fundamental basic building blocks, which can generalize later? Like how do you design tasks that are generalist in nature?
Yeah, so the question was a lot of kind of general NLP pre-training tasks are things like fill in the blank. Is there an analog in something like robotics? And in general, I mean, there are some things that are somewhat analog. So you can take video data from the robot's experience and have it interpolate frames, like say, predict this frame, or you can mask out part of an image and say, predict where, basically fill in this part of the image. And so you can make very direct analogs like that. And the approaches like that have shown some success in robotics, although there are also other aspects of robotics that make it very challenging. For example, in NLP, we have all of Wikipedia, and we don't have Wikipedia for robotics. We don't have data of robots tying their shoes or robots learning how to pour water just lying on the internet in massive quantities, and that brings up another challenge that is more readily solved in NLP. Yeah?
Is there any fundamental difference between like this multitask learning or I call this multitask a single task, and I do this single task learning?
Yeah, I'll get to that at the very end of the lecture. Yeah. Cool. So why should we care about multitask learning and meta learning beyond robotics and general purpose machine learning systems? And specifically, why should we care about deep learning in this context? So I don't think deep learning needs too much motivation these days if you've taken a machine learning class. But in terms of a couple slides, historically, the approach to things like computer vision was to design some features, to try to design mid-level features, and then tried to kind of train a classifier on top of those mid-level features. And there are many aspects of this kind of pipeline that were designed by hand. And then the more modern approach to computer vision isn't to try to hand design low-level features and mid-level features and so forth, but rather to try to just train a single neural network end-to-end, train the parameters end-to-end to do the entire task. And there are some benefits to the former approach. You get some notion of interpretability, for example. But in general, the second approach here works a lot better, which we'll see on the next slide. And it allows us to handle unstructured inputs, things like pixels, things like language, sensor readings, really any input that you can imagine, without having to understand, without having to engineer like really good features for that particular domain. So it allows us to perform tasks without a lot of domain knowledge. And as we saw over the years on the ImageNet benchmark, this is showing performance or error rate on the ImageNet benchmark between the years 2011 and 2016. Overall, we see a downward trend. But what's notable here is that this dot right here is AlexNet, which was the first end-to-end approach for the ImageNet competition. And everything after that is also deep learning-based approaches. And so we saw this really striking paradigm shift and also very striking shift in the performance that you can get on these kinds of computer vision tasks. In a completely different domain in natural language processing, if we take, this is a paper from, I think, 2016 or 2017. They're trying to use deep learning for machine translation. Before this paper, Google Translate was using something that wasn't doing end-to-end deep learning. It was called a phrase-based system. And so that's called PBMT, whereas GNMT was standing for Google's neural machine translation, which is an end-to-end approach. And we again see really large improvements, like 60 to 87% improvement on these different translation tasks. And now systems like Google Translate use exactly these kinds of models when making predictions, and they work. Well, there's still obviously lots of room for improvement in the translations, but they work far better than the previous systems. Cool. So that was some brief motivation for why we might focus on deep learning systems. Now, why might we focus on deep multitask and meta learning systems? So in deep learning, we've seen that if we have a large and diverse data set and a large model, that leads to good generalization on the tasks that I showed on the previous slide. We saw this with ImageNet, with things like transformers, machine translation. But there's a lot of scenarios where you don't have a large and diverse data set at the outset. There's scenarios like medical imaging where there are privacy concerns with sharing lots of data, or robotics where we don't have Wikipedia for robotics, or things like personalized education or translation for rare languages, where we don't have a large data set already sitting on the internet, and it would be very expensive and costly to try to collect a large data set. And so these are the scenarios where this kind of recipe will start to break down. And it's impractical to learn from scratch for each of these different circumstances, like for each rare disease, or for each robot, or for each person, or each language. Now, beyond that, there's also scenarios where maybe you have a large data set, but that data set is very skewed. So you have a long-tail distribution where this is showing kind of a histogram of the number of data points for different aspects or different parts of your distribution, different slices of your distribution. And these different slices could correspond to objects that the system has encountered, or interactions with different people, or the words that it has heard, or driving scenarios, and so on and so forth. And these kinds of data sets don't arise in a lot of machine learning benchmark problems, but they actually come up all the time in real-world applications. There's a lot of words, for example, that you hear all the time, and a very, very long tail of words that come up much less frequently. And this long tail of edge cases actually presents a major problem for modern machine learning systems. And I would argue that's why we don't have self-driving cars on the road today, because there's so many edge cases that come up in self-driving situations. And multitask learning and meta learning won't solve this problem in and of itself, but there is some signs of life that kind of indicate that if you can leverage some priors from the big data and try to translate that to the tail of situations, then you might be able to better handle these kinds of distributions. Cool. Beyond that, what if you want your system to quickly learn something new? This is, again, a scenario where you don't have a lot of data because you want to learn very quickly. You want to learn something very quickly about a new person, like a new user, or about a new environment, like a new environment that you've placed your system into. And for this, I'd like to actually give you guys a little test where I want you guys to learn something new. So in particular, for this test, I'm going to give you a training data set. The training data set is the 6 images on the left. And the far left images are all paintings painted by Brock. And the next 3 columns are paintings painted by Cezanne. And so your goal is to learn a binary classifier between paintings by Brock and paintings by Cezanne. So I'll let you train a little bit your classifier. And now that you've hopefully learned a decent classifier, your goal is to classify this test data point. And so raise your hand if you think this is by Brock. OK, and raise your hand if you think this is by Cezanne. OK, cool. So most people got it right. So this is indeed by Brock. And I tried to give you a little bit of time to train your classifier, but maybe some of you didn't converge. And you can see that it's by Brock because you can look at some of the styles of the edges here, for example. I picked this example not to be one that's a little bit harder, maybe closer to the decision boundary. And yeah, so this is an example of few-shot learning. And so you took a really tiny training data set with 6 data points and were able to generalize to a new data point. So how were you able to do that? So if you were to train a machine learning system from scratch, like a convolutional neural network, on those data points from scratch, it probably wouldn't have gotten the right answer, like many of you did. But the way that it was able to do that, or the way that you guys were probably able to do that is, while you may not have seen these paintings before, or maybe even paintings by these painters, you've learned how to see. You've learned how to recognize patterns in images, how to recognize paintings, and all of your previous experience allows you to learn new tasks with small amounts of data. You weren't starting from scratch on this problem. And so this is what's called few-shot learning, where your training data set has a few data points. It's small. And few-shot learning is something that you should be able to achieve if you leverage prior experience rather than starting from scratch. Cool. So each of these 4 things that we went over, if you have, you want a more general purpose system, you don't have a large data set, you have a long tail, or you want to learn something new, all of these are scenarios where ideas from multitask learning and meta-learning might be useful, and where these elements can come into play. Cool. So now, beyond why we should study it, there's a question of why we should study it now. And in particular, if you take some papers from the 90s, I think probably everyone was born by 97. But if you take some papers by the late 90s, maybe not. Is anyone born before 97? Or sorry, after 97? Oh, wow. I'm getting a little old here. Cool. Well, if you take a paper before most of you were born, it says things like, we can try to train tasks in parallel using a shared representation. Or we can try to do multitask inductive transfer, adding extra tasks to a backpropagation network. So they're already doing deep multitask learning in this paper. You can take a paper from '98 talking about few-shot learning. So the ability to generalize correctly from a single training example. When faced with the new things to learn, humans can usually exploit an enormous amount of training data and experiences that stem from other related learning tasks. From even earlier, from 1992, some folks like Sami Bengio and Yoshua Bengio, who you may have heard of, were talking about the possibility of a learning rule to learn to solve new tasks. So ideas from meta-learning. So a lot of these ideas aren't that new. They've existed for a pretty long time at this point. And yet, even though they've existed for a long time, they're continuing to play a major role in AI systems.
Does meta-learning also help model generalization? You have a large data set.
Yeah, so the question, yeah, I guess it's in Zoom, I guess, for the people who are remote. So does meta-learning help generalization even when you have a large data set? So in general, these methods will give you the most bang for your buck if you have a small data set, because that's where leveraging previous experience will be the most useful. If you have a really massive data set, then you will probably do pretty well just training from scratch on that data set. It's possible that some prior knowledge might come in handy if you have some distribution shift. Basically, if you have a large data set, but your test set is actually from a slightly different distribution, then you might be able to learn invariances from your previous data in a way that allow you to do better, even when you have a large data set. But in general, if you have a standard IID problem and you have a large data set, then things like prior experience will be much less useful. Cool. So now, what are some examples of actually looking at these kinds of systems in folks at DeepMind? They were training a system to do lots of different kinds of vision and language tasks. And they found that they could actually train a single model that could do something like object recognition, where in this example, they describe a chinchilla, then they describe a Shiva, and then they give it an image of a new animal, and it's able to recognize that that new animal is an image of a flamingo, and also describe where the flamingo is found. So it can do object recognition, and the same exact model can also do things like reading. So you can give it a few examples of images of numbers, like arithmetic problems, 2 plus 1, 5 plus 6, and so forth. And then if you give it a new image of, in this case, 3 times 6, it's able to both read the numbers and also complete the arithmetic problem. And again, the same model can also do yet another task. In this case, it's trying to count animals. And so here, it's given an image of a few pandas, and it's told that this corresponds to 3 pandas. And at the end, it's given an image of 4 giraffes, and it's able to count the number of giraffes and identify that they're giraffes. So what's really cool about this system is that it's not just specialized for one thing. It can do lots of different things, and it can do lots of different things in a few-shot way. So you're giving it a few examples of how you want to perform the task, and it's able to leverage that in order to figure out what you want it to do and ultimately do that task. So this is one modern example that was pretty exciting. One other modern example is a paper that I co-authored in 2021 that I personally was very excited about, where we were using meta-learning in an education application. We're looking at trying to provide feedback to students on work that they did, open-ended student work in a Intro CS course. And so in particular, the Code in Place course was a really massive online course that was offered by a few folks at Stanford. And at the end of the course, there were 16,000 solutions that students wrote up to the course. And grading 16,000, giving feedback and grading 16,000 solutions is a massive undertaking. And we were able to get volunteers to give feedback on around 1,000 of the student programs. But if you train on those 1,000 programs from scratch, you're not able to get a very good system, because 1,000 programs from scratch, these are Python programs that we're trying to give feedback on, that doesn't work very well. But with meta-learning, we were able to train on previous student data of taking exams and giving feedback on those exams, and use that meta-learning system, adapt to this new course with these new problems, and ultimately give feedback on the remaining. And so in particular, what it looked like is we were able to give a student program like the program right here. And there's a syntax error in this program that would make unit tests not useful at all. And so actually, there were a few thousand cases where unit tests were helpful, but most of the solutions, they were not very useful. And they were able to actually generate feedback. So in this case, the feedback is that there's kind of a minor error on getting the input from the user, which could be something like forgetting to convert the user input to a float. And the system actually worked really well, and it was actually worked well enough to actually deploy in this course to give feedback to real students, which wouldn't have been possible without some of the ideas that we'll cover in this course. So those are 2 examples, the Flamingo model and the education model. Yeah?
For the people who got the real feedback
The question is, can you compare the learning outcomes for the 2 groups? So we did actually do a blind A/B test with the system, and so 1,000 of them got human feedback, 15,000 got the feedback from the AI system. And the students agreed with the AI, with the meta learning system feedback slightly more, it was like 1% more. I think they agreed with it around 97% of the time, and they agreed with the human feedback around 96% of the time. Of course, they might just be agreeing with it because they like the feedback or whatever. And so we actually asked them also how useful it was. And they rated it as useful, on a scale of 1 to 5, I think they rated it around an average of 4.6 out of 5. So they found it useful. We weren't able to measure learning outcomes between the human feedback and the feedback from the system because this was towards the end of the course. It was kind of a diagnostic at the end of the course. We also didn't feel like it would make sense to withhold feedback from students to compare no feedback in the meta learning system. But I think the real win is trying to trying to give feedback in scenarios where it was otherwise would be very difficult to provide that feedback. Yeah.
Multi-objective problem using multitask learning. It's something like where we can't combine our objectives into a convex common objective. Is that possible using multitask learning?
Yeah, so multi-objective learning is, we'll cover it in the lecture on Wednesday, but it's basically, you can think of it as a subset of multitask learning, like a special case. Yeah.
Are there any applications for real-time or streaming data?
Applications for real-time or streaming data. I guess there's nothing, I could certainly imagine there being actually a lot of applications making sense, because if you have streaming data, you may want to adapt very quickly to the current circumstance that you're in with a small amount of compute and a small amount of data. So from that standpoint, things like few-shot learning may be very applicable. But I don't have, I haven't encountered, there's nothing that comes to mind immediately in terms of a specific application I've seen in the literature. Yeah.
So are we like trying to have some examples that adapt the models based on those examples, or like in the example you showed, like there was featured prompting, like multiple prompts, and it's basically the same network that is being generalizing to all these tasks, but it's not learning something new. It's just the same networks with different inputs that are being given to it. So is it the same thing, or like how do we think about these two things?
Yeah. So the question is, what's the difference between few-shot prompting and few-shot learning? And I think there's a very gray line. Like I don't think it's black and white. We'll talk about this a little bit in some of the future lectures. You can think of, we'll talk about it more in future lectures. I think it's not, it's unclear, it's fuzzy. Yeah.
Does meta learning always require a model that has previously been trained on some data? Because it feels like meta learning is adapting this model to a new set of smaller data. Or,
Yeah, so you're asking, does meta learning always require some previous data?
Or like, is meta learning just essentially adapting a model towards like newer data? If that makes sense.
Yeah, so kind of transfer learning and meta learning are, in many cases, trying to adapt to new circumstances. Maybe I'll move on actually a little bit, because I'll give kind of some definitions of what multitask learning and meta learning and transfer learning are, or at least what the problem statements are, and that might answer your question. Awesome. As a few more example applications of very recent use cases of multitask learning and meta learning, one from 2019 is looking at machine translation. It turns out if you, instead of translating between just one pair of languages, if you translate between lots of different languages, in this case 102 languages, you're able to surpass very strong baselines that are just trying to train on a pair of languages. So there's a lot of shared structure and a lot of shared information that you can leverage from those other data sets, or from data sets of other languages. And people have also been using multitask learning systems actually for multi-objective optimization, where you have multiple competing objectives in a YouTube recommendation system, and thinking about how do we optimize these objectives. And we'll actually consider a case study of this paper in the next lecture. So these are a little bit more on the applied side, a little bit more on the research side. There's also, I mean, there's lots of papers on these topics these days, and so I'm just highlighting a few, but one example is a paper called A Generalist Agent that was training on like really a really wide range of tasks. So ranging from dialogue systems to playing Atari games, to controlling a quadruped robot in simulation, to controlling a real robot arm. And so they were able to find that you could actually stuff the data of all these different tasks into a single model to have it do all of those different tasks. And lastly, I guess I showed this example on one of the earlier slides, but you can also apply this in examples in real robotics where you want a robot to take experience from previous tasks, or sorry, from previous objects, and ultimately perform a task with a new object. So in this case, the robot hadn't seen this red bull before, or this peach before, or the distractor objects for that matter, and is able to figure out that it should place the object into the red bull in this case. Cool. So those are kind of a few modern examples that are quite interesting. Yeah.
Is there any study looking into trying to understand those generalist kind of models, like the different tasks that they train the model to more maybe disentangle them, or are they something that like a true generalist like kind of model that is able to have understanding of the task that they perform?
Yeah, so the question is there work that tries to understand what these multitask learning systems are learning and if they're disentangling the tasks in some way? In general, I guess there's no particular paper that comes to mind, and I think that it's also a very challenging question because we don't have good tools for interpreting neural networks and what they're learning. I think the biggest tool is actually just to observe its behavior on new inputs. And so, for example, if it's able to generalize to new tasks effectively, then that's an indication that it's not learning the task completely separately, that it's actually learning the shared structure. Whereas if it's completely unable to generalize to that new task, it's maybe an indication that it's not learning kind of a unified representation of those tasks, or that the new task is just too far out of distribution compared to the previous tasks. Yeah.
So the one-shot annotation basically overfitted? Why is it considered like impressive from a research standpoint?
So in this case, this paper is from a few years ago, but it's certainly, in this case, overfitting to the task of placing, I guess. I mean, overfitting is a term that means many things oftentimes, but you can think of it as that. I think what's interesting about it is at least this paper was one of the first examples of just looking at a raw video and actually interpreting that raw video to figure out how to do the task. And I think that we've also seen, certainly since then, seen more interesting and more impressive things being done with few-shot learning. Yeah.
Yeah, I was just wondering about this one-shot annotation learning paper because, like, in general, how do you know that the human intended to put, like, the ball into this specific cup, even when the orientation was changed, versus like always putting it in the bottom left place, right? Like, how should an AI consider like these different tasks?
Yeah. So the question is, it seems like this task is a little undefined. It's unclear from a single example whether the goal was to put the peach exactly right here, or if it was to put it into the red bowl, or maybe there's other ways to interpret the video as well. And the reason it's able to do, at least in this case, what at least to me aligns with human judgment is by having prior data. And so if you only gave it this one example and learned from scratch, the problem of inferring the intent is actually mathematically underdefined in many different ways. You could there's also, especially from images, it's especially underdefined because it could be that you wanted to change the pixels here to be orange, for example, and maybe that doesn't involve moving the peach there. So it's underdefined if you learn from scratch, but when you have previous data and previous experience with other objects, you're able to leverage that previous experience to figure out what exactly was intended here. So in this case, the previous example involved placing into containers. And in each case, it was trained to generalize to place into the container rather than place the object in the same position. And instead, if you gave it previous experience that said, if I see a demo like this, then place it in that exact same position, it would instead learn that from the previous experience. But yeah, cool question. Okay, and then one other thing that I think is important in the context of why we might study these methods now is I think that it's important for making methods in deep learning accessible to many different people. I mentioned that deep learning works really well when we have a large data set. And if we take some of the most common data sets that are out there, like ImageNet or these machine translation data sets and so forth, they have a lot of data in them. ImageNet has 1.2 million images. This data set of English to French translation has 40 million paired sentences. And the switchboard data set has 300 hours of labeled data. And so this is a lot of data. And so if these are exactly the problems you care about or the data distributions you care about, you're in great shape. But a lot of problems that we look at don't have this amount of data. And so, for example, if you look at Kagel's diabetic retinopathy detection data set, this only has 35,000 labeled data sets. 35,000 labeled images. And this is something where deep learning isn't going to work as well if you train from scratch on this. And likewise, there's a data set on trying to adaptively treat epilepsy, and this has less than an hour of data. And one of the papers that I showed before from the beginning of my PhD, where we were learning the spatula task, this had less than 15 minutes of data. And so this is much, much less data. In many applications, we don't have tons of data. Or maybe we're looking at a population that has a lot less data of it. One reason why I think that things like multitask learning and meta learning is important is if we can extract prior information from other data sets that are larger, then we might be able to actually start to better solve tasks that have much less data, which will in turn make this kind of technology accessible to people who don't have the money to collect a huge data set or don't already have a data set collected for their problem. Yeah.
Is there a standard way to quantify how useful data from one task could be to learning a new task?
Yeah, so the question is there a way to quantify how useful data for one task might be useful, how useful it is for another task? And I guess the short answer is that's an open problem. It's a really useful and interesting problem. The short answer is it's unsolved, but there is some work on it, on trying to relate the similarity between two tasks. And it's actually not really a similarity function, it's more of a directional similarity, like how useful is one thing for another thing. There's also some work just purely on data valuation in general, like how valuable is a data point in the context of a larger data set. And so like James Zhu, for example, on campus has some work on that as well. Yeah.
You talked a lot about transfer learning with like going from a large data set and then applying it to a smaller data set. Are there any examples that you see in the literature where you take a large number of tasks each with small numbers of data, and then leverage like the common aspects of them to achieve better performance on all them together than just one individually?
Yeah, absolutely. So the question is, a lot of the examples we've talked about, you have a large data set and a small data set. What if you have lots of small data sets? And absolutely, we've seen examples where these kinds of techniques can be super useful in that scenario. Actually, in your homework, we'll be working with the Omniglot data set, which has about 20 examples of each character, but lots of characters, so around 1,200 characters, or actually more than that. And so that's an example where these kinds of systems can work quite well. And there are other examples as well where we can sort of like amortize the cost of learning. Yeah.
How helpful is it to use machine learning models to generate data sets and then use those generated like synthetic data and try to use that data set? For example, with robots, I thought about maybe OpenPose, where you can actually get the joints of the person, and maybe that's helpful for robotics. So maybe that way we could generate a ton of data, because I'm sure we have a lot of information for humans. So is that something that's applicable or common?
Yeah, so the question is, can we generate data sets, and is that useful and applicable and common? There's a little bit of work on that. So like Phil Isola, for example, has been doing research, a little bit of research on that topic. In general, there's possibly kind of a no free lunch thing where basically, if you're learning to generate data from a data set, then you're not really creating additional information when you train that generative model, and so that might not be more useful than the original data that the generative model was trained on. So from that standpoint, it's a little bit tricky, I think, to get value out of that sort of thing. But if you have domain knowledge that you can put into the generative model, that might help. So yeah, I think it's an interesting problem, and there have been a few works that have done kind of interesting stuff along those lines that I could talk about in office hours, like data set distillation, for example. But in general, it's tricky. Cool. So I've talked about a few different successes and a few different exciting applications of these kinds of systems. But I'd also like to emphasize that there's also lots of open questions and challenges. And we've seen some of these in some of the questions, like how do we determine the usefulness of one data set for another? And I think that also makes it equally exciting to study because it means that there's open problems that we can solve and that all of you can solve. In the last 15 minutes or so, I'd like to dive into what actually a task is and what multitask learning is. And we'll do this fairly informally in this lecture, but more formally define things in the next lecture. So informally, we can think of a task, or rather a machine learning task, as something that takes as input a data set and a loss function and tries to produce a model. I think this is a useful way to think of, or a fairly intuitive way to think about a machine learning task, because when you want a machine learning system to solve a task, you typically give it a data set and a loss function and optimize that to get a model. And different tasks can vary in a number of different ways. At a high level or kind of intuitively, you could have different objects, different people, different objective functions, which was mentioned, different lighting conditions, different words, different languages. So the different tasks that you might throw into a multitask learning system might be fairly varied, and they could vary along lots of different axes. And so the reason why I bring this up is that multitask learning doesn't just cover what you might think of as different tasks in terms of the English definition of the word task. It could also mean that, like typically you don't think of different objects as different tasks from the English definition of the word task. But if you want a system that can handle lots of different objects, and you might want to train it across lots of different objects, that might still pertain to this more technical definition of a machine learning task. But as I kind of mentioned this, there's one really critical assumption that comes up with these kinds of systems. And the bad news about this assumption is that the tasks that you train on, they need to have some shared structure. If they're completely independent from one another, then you won't get any benefit from training together, or you won't get any benefit from trying to exploit the shared structure. And if you don't have any shared structure, if they're completely independent from one another, you're better off just using single task learning. The good news, though, is that there are many tasks that have shared structure. And so as one example, if you consider the task of unscrewing a jar, a bottle cap, or even like using a pepper grinder, for example, using a pepper grinder and opening a water might seem very different tasks, but they all involve a very similar motion. And even if the tasks are seemingly unrelated, the laws of physics underlie real data, and so there is already a lot of common structure there, unless maybe you're on a different planet or something. And I mean, the laws of physics won't change there, but gravity might change, for example. People are all organisms with intentions. The rules of English all underlie all English language data. Languages are all developed for similar purposes, so even across languages, there's a lot of shared structure, and so on. So I think that there are actually very few cases where some tasks that you come up with are independent in a statistical sense. And so with that, the model can, or these kinds of methods can pick up on the shared structure and leverage that in order to do better. Cool. Now, yeah, question?
For a model like Gato that was trained by DeepMind, it was able to handle both, let's say, language and images. So what is the shared structure in that, and how is the model learning in that case?
Yeah, so the question is, in a model like Gato, it was doing both tasks that involve language and images, and what is the shared structure there? I actually think that in that particular case, the Gato paper didn't show significant signs of being able to, like significant indications that it was actually learning shared structure between those two things in terms of generalization. And so it's not actually clear to me that it was learning shared structure across images and text. And I could also imagine that it may be easier for the model to learn shared structure if, for example, you gave it images of text rather than tokens of text, because those modalities are very different from one another. It's kind of like if instead of, well, for us humans, we see everything through the same exact embodiment through our eyes and so forth, and we're never like getting one-hot vectors of tokens just passed into our brain. And that's kind of what neural networks get. They don't see things in a unified way, and so yeah. The short answer though is that it's unclear if it was actually learning shared structure between the two. Although there is some work that has actually found that you are able to learn a shared space, at least a shared embedding space with images and text that is more unified. Lots of questions in the back. Yeah, so the question is, how do you quantify the amount of sharedness? It's difficult to quantify given a pair of data sets, but one way that's nice to think about, that we'll talk about in the Bayesian meta-learning lecture, is from the notion of kind of Bayesian graphical models. If you have two random variables, if they're independent from one another, then they don't have any shared structure. Whereas if there is some dependency between them, if there is an edge between them, or either direct edge or an indirect edge, then they do have some shared structure. Quantifying how much shared structure they have is hard, although conceptually I think that thinking about it from that Bayesian standpoint can be useful. Yeah?
In the case that we don't find any shared structure, would we argue that the model is actually learning two separate independent models which could be trained separately and still do the same thing?
Yeah, so if there isn't any shared structure, the model might just basically learn to use half the model for one task, half the model for another task. And I guess there actually isn't that many downsides to that, but there also aren't any upsides to that as well. Yeah?
In terms of the shared structure, is it necessary that the tasks that we're training on have shared structure, or would it also be fine if like the task that we're trying to generalize to is related to both of the tasks independently, but the tasks that we're actually training on, they don't have any like overlap, if that makes sense?
Can you repeat that?
Yeah, so if like the task that we're trying to generalize to is task C, and that relates to both A and B in some way, but A and B themselves maybe are not that related, but we're actually training on A and B to generalize to C.
I see. So if you have two tasks that are unrelated and then you want to learn a new task that's related to both of them, so for example, if you want to task A is to pick up a fork, task B is to use the fork to skewer something, and then task C is to pick up the fork and skewer something. There are certainly instances where things like that come up, and so I would say that, yes, that's a scenario where these kinds of techniques make sense. Although some techniques will be more useful than others. Yeah?
Since you were talking about modality, do you suggest that when we use a multitask model, do they belong to the same modality like text or image, or can we have a combination of both of them?
Yeah, so the question is, can you kind of have a combination of multiple modalities? And in some sense, the Flamingo model that I showed before is actually already an example of a multimodal model that takes as input both images and text. And so yeah, you could definitely have tasks, and Gato is another example where different tasks do have different data modalities. If you are representing those modalities differently, then the shared structure, it may be harder for the model to find the shared structure. But certainly something that's possible with these models. Cool, I'm gonna try to move on a little bit. I think I only have a few more slides, and then we can take a little bit more questions at the end. Cool, so what are some of the problem definitions that we'll cover in this course? So Informally, we can think of the multitask learning problem as learning a set of tasks and generally trying to learn that set of tasks more quickly or more proficiently than learning them independently. And kind of here, the set of tasks is this. We see the same set of tasks during training and during testing. So we're not trying to handle a new task. In contrast, the transfer learning problem is we're given data on previous tasks, and our goal is to learn a new task more quickly or more proficiently. And this is also the problem that meta-learning algorithms also aim to solve. And so basically in this course, we'll be looking at any kind of method that tries to solve one or both of these problem statements. Now, one question that came up earlier is that doesn't multitask learning reduce to single task learning? So one thing that you could do is you could say you have a data set for each task, di, and you have a loss function for each task, li. Can you basically sum up your loss functions, combine your data sets to create a data set and a loss function, and then you have a single task learning problem where you have one data set and one loss function. So are we done? So in some sense, it can reduce to a single task learning. And aggregating the data across tasks and learning a single model is one very viable approach to multitask learning. The transfer learning problem where you want to learn new tasks is what we'll focus on more in this course than multitask learning because it is a little bit more challenging. And this solution, it doesn't just reduce to single task learning, but we will have one lecture on multitask learning on Wednesday where we'll cover other things like how do we tell the model what task we want it to do, or what if aggregating the data set and training on all of it doesn't work. So yeah, we'll focus more on the second problem statement, but there is also still some challenges that come up in the multitask problem statement beyond just training a single model with a single loss function. Cool. So that's it. Let's see. We could take a few more questions as a group, but I also maybe we could also just take questions up in front if people have additional questions, and we'll end there. As a couple of reminders, Homework 0 is out, and it's due on Monday next week. And if you want to work in a group for your final project, we'd encourage you to start forming project groups.